Hi there, welcome back to our course on advanced quantum mechanics. This is lecture 30. Remember, we have been considering the situation where we have a system A, a system B, and we also considered the quantum system AB, which is containing A and B as subsystems. Now, quantum system AB, obtained by taking a larger Heisenberg cut, is just a regular quantum system. Just like everything in the universe is apparently quantum mechanical, so is our system AB. And therefore, our quantum system AB has a Hilbert space. Let's indicate it with H superscript AB associated to it. And in that on that Hilbert space, its operators act, its observables act. So for example, we could have some observable, let's call it F hat with a superscript AB, to indicate that it acts on the Hilbert space HAB. So it's observable of the big system. If this is a self-adjoint operator, then by the spectral theorem, it has an Eigen Basis, and that Eigen Basis could be called FABN. Let's assume that it's that our observable here has a completely discrete spectrum, so it has only a point spectrum. And so we can enumerate the basis vectors like this. Well, then they form a Hilbert basis for HAB. Here's a Hilbert basis for HAB. Everything is as usual as for any other quantum system. Also, it of course has a Hamiltonian. Let's call it H total. We could also call it H hat superscript AB, but let's call it H total for the total system here. That's just common terminology. And it acts on the Hilbert space HAB. Also, our total system has a density matrix, and that density matrix is denoted by rho superscript AB, and it too acts on the Hilbert space of our total system. Of course, it could be that this is a mixed state density matrix, but it could also be a pure state density matrix. Now, what we've been after is understanding how, in quantum mechanics, we can describe the change of Heisenberg cut. So for example, in this case here, we would like to understand the subsystems in terms of the big system, or how the two subsystems combine to form the big system. What's the relationship between the whole and the parts, between the entire thing in system AB and its constituents? Now, what we found so far, we found the following. We found that if psi is in the Hilbert space of our subsystem A, and phi is in the Hilbert space of our second subsystem B, then we have that the tensor product, which we defined in the previous lecture, is a vector in the big Hilbert space. I mean, in the Hilbert space of the big system AB. And all those vectors are what are called unentangled vectors. Unentangled vectors. Now, linear combinations of these vectors are called entangled. Now keep in mind that the word entangled, the definition of entanglement, always assumes that we have a situation like this, where we have subsystems and a total system. And then in that situation, we can ask, to what extent is the state of our system, AB, entangled or not? And this is the definition here. At least it's the definition of whether or not a state of the total system is an entangled state or not. If you don't subdivide your system, then the notion of entanglement makes no sense. The notion of entanglement is always relative to a subdivision of a system. By the way, what we are studying for now is binary entanglement, where we divide our system into only two subsystems. You could also subdivide your system into more subsystems, and then the notion that describes that situation is called multipartite entanglement. All right. We also saw that there's a tensor product not only for vectors, but also for operators. And this led us to this observation, namely that if f had superscript a, so I will most of the time now use superscripts to indicate what Hilbert space these operators are acting on. At least I'll use it whenever it might otherwise be ambiguous. So if f hat superscript a is an operator that acts on the Hilbert space of system A, and if f hat b is an operator that acts on the Hilbert space of system B, for example, there might be two observables, then the operator defined by f hat A tensor f hat B acts on the Hilbert space H superscript A B. So this is now an operator, as the case may be, an observable perhaps, which acts on the Hilbert space of the total system. And how? Well, if we have f hat A tensor f hat B, and we want to apply that onto a vector of the total system, which could be, for example, some vector psi tensor phi, just to write down an unentangled one. If we want to, we can write down a linear combination of these guys to get an entangled state too. This will just extend linearly as usual. So if we apply this operator on the big system's Hilbert space onto that state of the big system's Hilbert space, then this is, by definition, the action of f hat A on psi. This is well defined because that's a state of the system A and that's an operator of the system A. So we can assume this as given tensor, and then, oh, it's not a G, it's an F. F hat B acting on this state of system B. And that thing, of course, is again an element of H AB. Now, all this we covered already. Let us now move on to bases of HAB from basis for HA and HB. The point is that if we have a Hilbert basis for the Hilbert space of system A and a Hilbert basis for the Hilbert space of system B, then we should be able to get a Hilbert basis of the total system, and indeed that's the case. So assume that the vectors AN are a Hilbert basis of HA, and similarly Bn for HB. Now, then we define the vectors omega n m defined to be an tensor Bm are of course elements of the Hilbert space of the big system because of the tensor product, but more than that, they actually form a Hilbert basis. One can prove that, but we're not going to go through the formalities there. Then these form a Hilbert basis of HAB. And of course, we will write it as omega n m. Notice that curiously, this Hilbert basis can be enumerated, right? Can be counted. I mean, we are assuming here that these guys can be counted, have a discrete index n. Now those also can be counted, but we have two indices. That doesn't make the Hilbert basis any bigger because countable infinite is countable infinite. There are no two different kinds of countable infinite. There is the Cantor diagonal trick, which shows that if you can count to infinity once, you can also do it with two indices. You can reduce two indices to one index. All right, so we have a Hilbert basis now of our Hilbert space for the big system. And that means we can now write down a resolution of the identity. So, very important, obtain a resolution of the identity. So whenever we have Hilbert bases A and AN and BN for the subsystems, they give us a Hilbert basis for the big system and correspondingly also a resolution of the identity. Namely, the identity operator, and for now, let me write down here AB to indicate this is the identity operator in the Hilbert space HAB. But in the future, I will drop some of those indices, namely whenever it ought to be clear from the context what Hilbert space the operator acts on. So this resolution of the identity is then sum over all n and m of, well, the ket bras of all of the basis vectors. Now, this can be spelled out more explicitly because remember the omega and m take this form. So therefore, this resolution of the identity can also be written as the sum over n and m. And then we have here the an and bm and an and bm. And well, just a sec, I have to move this a little bit. I will later explain why I forgot to write a tensor product here. Oh, and similarly here, there is a tensor product in here. Actions, ungroup, there we go. All right, so in principle, there ought to be a tensor product here. And there ought to be tensor products in here. Oh, so many tensor products. Okay, so the point I want to make is here that remember how it is when you write down 7 times x? This is really 7.x, right? Multiplication used to be written in primary school with a dot. But then at some point we gave up on writing the dots. It's similar with tensor products. In principle, when we write down a cat bra, as we've done previously in the course, we actually wrote down a tensor product because this vector here, switch back to red. Okay, so this vector here is actually a vector in H, AB, tensor H, AB star. So in principle, we have used the tensor product all along. We just never bothered to write it out and spell out all its axioms. But now that we know its axioms, we know that actually we have the tensor product occurring all over the place here. And we will in the future often omit the writing down of the tensor product symbols. It's understood that it ought to be there. The rules of the tensor product apply, whether it is between ket vectors, between bra vectors, or ket and bra vectors. All right, so what we have is that the identity, a resolution of the identity in the Hilbert space of the total system can be written in this way here. And let us give this equation a name. Let us call it equation S, because we will have to refer to it back. We will later refer to this equation again. Okay, so we have a resolution of the identity in terms of the basis vectors of the constituent system. We can now use the resolution of the identity in the same way that we've used it before. For example, to write some abstract equation in a basis. So for example, for some vector, let's call it gamma, in the Hilbert space of the combined system, we have now that gamma is certainly 1 times gamma. But this is all of that applied to gamma. So we can just copy this. Copy and paste. Yeah, well, So sum over n and m, and then here we apply this resolution of the identity to the state gamma. And this means that we obtain that gamma is equal to the sum over n and m, and then coefficients gamma n m, the wave function of our abstract state, in the basis of this resolution of the identity, times an tensor bm. We will soon drop writing these tensors here, where these guys are just numbers with the wave function being equal to an tensor Bm. This is a vector in the dual, right? This is an element of the Hilbert space AB dual, and that contracted with gamma, which is inside the Hilbert space HAB, right? Because that's this part here, right? Gamma NM, that's this. This is equal to gamma NM. And this part here is left over. That's what we have here. Okay, so we have now expanded an abstract vector of the Hilbert space of the big system in terms of a basis, and we got a wave function for that state, for that basis here. And notice that what we find here is that this gamma has a wave function. It has two indices. But the reason why it has two indices is that we broke up our total system into two subsystems. Of course, we could still also choose to write down a wave function for gamma, which has only one index. So alternatively, could choose Eigen Basis. Let's call it the vectors f, a, b, n of f hat a, b. Remember that was an observable of the total quantum system, and this is its eigenbasis. Then we have that the resolution of the identity of our total system can be written as the sum over n, and then fn ab, fn ab as usual, and therefore we obtain that our state gamma is equal to the sum over all n, and then we have gamma, let's call them tilde now, not to mix them up with the other ones, n, and then fn ab, the basis vectors, with gamma tilde n equal to fn ab gamma. Right? We obtain that simply by multiplying the identity, the resolution of the identity onto the gamma. We obtain this straightforwardly. So what we see here is that when we break a system into two subsystems, conceptually, then we can obtain wave functions for its states that have two indices rather than one. If we broke our system into 27 subsystems, then yes, the wave function would have 27 different variables here. But of course, we can also just do the usual thing, and then we have wave functions that depend on one variable. Now, the situation is similar for operators. Similar for operators on the Hilbert space HAB. Namely, let's say, assume Q hat acts on H superscript AB. Then on one hand, we can write that Q hat is equal to identity, Q hat, identity, and we can choose a resolution of the identity. I won't write AB here, it's understood now that this is all happening in the Hilbert space AB, we can use the resolution of the identity, which is provided by the Fn, as usual. Then we would have sum over n and n prime, and we have the Fn and Fn q hat, that's the identity from the left, and then we have the Fm, that's the identity, no, not n, we chose to call them n prime, right? So n and n prime, n prime, n prime, and all of these are AB, and AB, and AB, to indicate that these are eigenvectors of an observable which lives in the big Hilbert space. So then these we would call, as usual, the matrix elements of our operator Q hat in the Fn basis, and there we go to indices as is usual for operators. But we can also write Q hat equal to 1, Q hat 1, and then use the resolution of the identity that we had above, namely in terms of the in terms of the basis of the subsystems. So then that means we now get, oh, I think I need more space for this, so I write it down here. So this will then be the sum over n and n prime, m and m prime. And then we have an and bm, and I'm dropping the tensor product symbols now, and then an bm, that's the first resolution of the identity, the one on the left, and then we have the Q hat operator, and then we have an prime b m prime and an prime b m prime. And then these numbers, remember the bracketing should really be like this. This is a vector in the Hilbert space on which the Q hat acts. And that is a vector that acts on the Hilbert space on which Q hat acts, but it's a dual of it. So these are numbers that we call Q hat, and then n prime, m prime. So now an operator has 4 indices. Right? Just like the vector has 2 indices, the vector wave function has 2 indices, now the operator has 4 indices. Okay, so now we know how to write vectors and operators in the various choices of bases. This means we are now ready for the main question that arises with having a big system, AB, that contains 2 subsystems, A and B. Namely, if our big system AB is in a state rho hat AB, then the subsystem A will be in a state rho hat A, and this will be in a state rho hat B. And the big question is, what are they? What are rho hat A and what are rho hat B given rho hat AB? It's clear that if we're given that density matrix, then we can calculate all observables in the big system. So therefore, we should be able to calculate all the observables, including those of subsystem A, including those of subsystem B. And if so, Well, then it means we must implicitly somehow know what the density matrices are of system A and of system B. So there's got to be a relationship between those density matrices. And what is that relationship? So we will need a tool. We need the tool of so-called partial traces. In order to calculate what rho A is from rho AB. Now, let's start by remembering how an ordinary trace works. Recall the usual trace. Assume that G hat AB acts on the Hilbert space H AB. So this could be an observable, or it could be a density of state, it could be a density matrix, and so on. Then the trace of G hat AB can be calculated as usual, choosing, for example, our basis of the Fn. So this would be Fn superscript AB. Remember, F hat AB was some observable of the big system. And we calculate the trace by summing over the diagonal elements in the basis F of the Fn. So AB. Here we are summing over all the diagonal elements. This is the trace as usual. But also, we can use other basis vectors. Not these. We can choose any basis vectors in the big Hilbert space that we want, including the basis vectors that are constructed by the tensor product out of the basis vectors of the subsystem. So therefore, we can also write this trace. So the trace of G hat AB, we can also write it as the sum over n and m. And then we write the basis vectors that come from the subsystems. Remember, these guys are basis vectors as well for the big systems Hilbert space. Acting on G hat of AB. And then again, here we have AN and BM. I will later drop those big brackets there. Okay, so this is the usual trace. Now, the partial trace. Say over subsystem B is defined this way. It's simply when you calculate the trace this way, except that you drop the sum for the A basis there. You don't do that one. So the trace, the partial trace over the subsystem B of the same operator here is by definition the sum only over the m's, and we have only the vectors bm acting on the g hat ab and then the bm. So you see the an are missing, and we're no longer summing over n as well. Now, the trace of an operator is always a number. In fact, a basis-independent number. But the partial trace of an operator, where we trace only over one of the subsystems' bases, doesn't give us a number. This thing is not a number. It is still an operator. This is an operator that acts on the Hilbert space of system A, because we have not contracted here. We have not formed any scalar products with these ANs. So notice the trace of B of G hat AB is an operator that acts on the Hilbert space A. Similarly, we can define the trace over subsystem A of our operator in the big system. And then that's, of course, the sum over all n, and then we have the an g hat ab. An is an operator that acts on the Hilbert space HB. Now, there's an important consequence that we can read off from this. That's sort of a trivial consequence, but it's important, which is that when we perform a partial trace, as we did here, we traced over only subsystem B, then we obtain an operator that acts on the Hilbert space A, and then if we do the trace over subsystem A, then in total we have performed the total trace. Right? Because in order to get the partial trace, we just did the tracing operation incompletely. If we then complete it, we get back to the usual trace. So notice we have that if we do the trace over subsystem B of G hat of A B, then we obtain an operator that still acts on system A. And then if we take the trace with respect to subsystem A of that, in fact, we wouldn't even write subscript A normally because it's no longer ambiguous, because there's only one system left, system A. But if we do this, if we first trace with respect to B and then trace with respect to A, then this is just simply the total trace of G hat A B. And of course, we can also write it in this way. It's the trace where we first do the trace over subsystem A and then subsystem B, G hat A B. Okay, so that's something that will be very useful when we now address the question of moving the Heisenberg cut. Moving the Heisenberg cut. So instead of drawing the boundary between the quantum system and the rest of the universe around system A, we will draw it around system AB. And how do we then translate the quantum mechanical description of the big system to the quantum mechanical description of the smallest, the subsystem, and vice versa? What's the mathematical connection there? And as you may have guessed, that has to do with the partial trace operation. Let us ask the crucial question now. Question. Given the density matrix rho hat of the system AB, what is the density matrix rho of system A? If we can calculate that, we can also calculate the density matrix of system B, of course. So how do we answer that? Well, we start with the following observation. Recall. Rho hat A is that operator which obeys that f that the expectation value of an observable in system A is equal to the trace of system A. It's kind of redundant to write it, but just for clarity, let me put it there. Trace of system A of the observable. Remember, this is not the same f hat that we had above, because the f hat above had a superscript AB. It was an observable in the big system. Now our f hat is just the name of an observable in the system A, times the density matrix rho hat A, right? So this is for all f hat A and rho hat. But okay, that's what we wanted to say. So the rho hat A is that operator for which this is true, this equation is true for all observables. We know that from earlier in the course, right? That this is how you calculate the predictions for an observable. Namely, you'd calculate the trace of the observable times the density matrix. All right. Let's keep that in mind. Rho hat is that operator for which this is true for all observables. Now, calculate for an observable of subsystem A, the expectation value with the big Heisenberg cut. i.e. With i.e. from the perspective of system AB. Right, so this is the small Heisenberg cut here. Let me just write that here again. So this is small Heisenberg cut around A only. Right, so if we're looking at just system A, then it has its density matrix, it has its observables, and its expectation values are calculated as the trace of the product of density matrix and observable. Now, that's not our starting point anymore, because we have a bigger Heisenberg cut. We are now cutting around A and B. And now from the perspective of this bigger system, AB, how does this look like? Well, recall from previous lecture, the observable, what happened there? Accidental writing, observable f hat A is represented on HAB as f hat A tensor the identity. This thing acts, this operator acts on which acts on HAB, right? Okay, so that's our observable in the big system. So now we have everything we need, namely, so in system AB, we have, I shouldn't say even, I should say for. For system AB, we have state is rho hat AB. Observable of interest is f hat A tensor 1. This observable is self-adjoint, right? Because f hat A is and the identity is. All right, so the prediction is, well, f superscript A expectation value now calculated for the big system using this observable here is given by, as always, the trace of observable f hat A tensor 1 times the state, times the density matrix, rho hat AB. Now let's work out what that is. Well, first of all, we know that we can obtain that by tracing carefully, namely first tracing over B and then tracing over A. So it's the trace over A of the trace over B of the observable f hat A tensor the identity rho hat AB. I just wrote here that the trace is obtained by first doing the partial trace over B and then doing the remaining trace over A. Oh, sorry, this is okay. So we carry out that first trace, so it's the trace over A, and then that trace is the sum over the diagonal elements. So it is sum over all M, and then basis vectors in system B, we call them BM. It doesn't really matter which basis we choose there. And then f hat A tensor the identity, rho hat AB, that's our operator, and then we have the BM. Okay, so we worked out what the trace actually is here. Now, this is the trace over A of, and now we notice that the BM are only acting on the second tensor factor here. Now, what does that mean? It means that since the f hat is non-trivial only on the first tensor factor, we can write this as the sum over M, and then we can pull out the f hat of f hat A, and then we have the BM and the, oh, not the F, it's a rho now. It's a rho hat AB BM. Now, remember that this, after this summing over, is still an operator in A. This is not number valued, right? Because this rho hat is an operator in that acts on the Hilbert space HAB. So then this is the trace over A, and by linearity, we can also write this as F hat A times the sum over M, and then the BM rho hat AB BM. Now we recognize something, namely this here. This here is the partial trace, right? So this is equal to the trace over B of rho hat of AB. And therefore, we can write this as the trace over A of F hat A, and then the trace over B of rho hat AB. All right, so the calculation was so long that we lost the beginning of it. This is the expectation value of, this is the prediction. This is FA predicted. That's this, okay? So, big Heisenberg cut. Therefore, we have this. Now, recall something we said up here, namely that rho hat A, the density matrix of subsystem A, which is our target. This is what we want to calculate. Rho hat A is that operator which obeys that the predictions for any observable are calculated by calculating the trace of observable times density matrix. This is, we know that from the small Heisenberg cut perspective. We know how to treat systems A. Expectation values are calculated by calculating the trace of observable times density matrix. So the desired rho hat A is that operator which obeys this for all observables. And now what do we have here? We have that for all observables, the expectation value can be calculated as the trace over system A. That's what we have here, trace over system A of observable F hat A. We have that here too, observable F hat A. And then this mysterious thing here. This mysterious thing must be rho hat A, right? So recall from small Heisenberg cut, that we have that F A bar is equal to the trace over system A of F hat A rho hat A. All right. And both of these equations are true for all observables. So for all F hat A, for all F hat A. And therefore, we conclude that given the state rho AB of system AB, the system, the state of subsystem A, rho A, must be the partial trace of the total state when you trace over system B. So therefore, we conclude that given the total state of system AB, we can calculate rho hat A through, and now that's the big equation, through rho hat A is equal to the trace of the subsystem B of the total state. And of course, similarly, the state of subsystem B is obtained as the trace over subsystem A of the total state. All right, so this is super important. Let's do an example. Assume the state of system AB is pure. Also, case 1, the state, which we can write as omega, is, let me just write it completely so that there is no possibility of misunderstanding. This pure state, let's call it omega, is unentangled. So we can write omega as psi phi. Should be a tensor symbol, but it's implied. By the way, the notion of entanglement or not entanglement is more tricky when the total system, when system AB is in a mixed state. And we won't go into the details of that. We will always assume that our total system is in a pure state. So assume that the system, the total system AB is pure, and that pure state is called capital omega. And case 1 is that this pure state is unentangled. So we can write it in this form. So therefore, the density matrix, therefore the density matrix of our total system is equal to omega, which we can also write as psi phi psi phi. Now, what then is rho hat A? Well, rho hat A, the density matrix of subsystem A is, by what we just calculated, the trace over subsystem B of rho hat AB, which we just calculated. So what is it? Let's see. It is the trace over subsystem B of psi phi psi phi. this is the sum over all m, and then we have here the bm, and then we have psi, phi, psi, phi, and then the bm, right? We're forming the trace over just the second Hilbert space, only over with the bm. And by the way, here you notice that in principle, it would be good to use tensor products, right? Because then it would become a bit clearer because of the axioms that the tensor products obey, that this thing here is actually seeking out something in its own tensor part of the Hilbert space. So this thing will contract with the phi, and because this is of system B, and that is of system B's Hilbert space. And this is of system B's Hilbert space, actually the dual of system B's Hilbert space, and that is of system B's Hilbert space. So what we obtain is that this is equal to sum over m, and then the psi and the ket and bra psi come out because they have nothing else to evaluate against. So we have psi, psi, and the rest becomes numbers. Namely, we have the bm catching this phi here, and then that phi catching that bm. Phi bm. Now, this we can write like this. It is psi, psi, sum over m, and then let's just reorder the two. They're just complex numbers anyway. So we have phi bm, bm, phi. And that's, of course, a resolution of the identity. So therefore, this is equal to phi, phi, which is equal to 1. So therefore, this is psi, psi. So we calculated that the state of system A is actually what one might have expected. We have that if the total system's state is a tensor product of a state of system A and a state of system B, then, well, if we calculate what is the state of system A, then it is just a state psi, because this is the pure state density matrix. And similarly, and of course, we obtain that rho hat B is equal to phi, phi, similarly. So, so far so good. This is for pure states that are unentangled. So the conclusion that we draw from this is that if rho hat AB is pure and unentangled, then it follows that rho hat A and rho hat B are pure. By the way, remember that it makes no sense to ask whether rho hat A is entangled. It makes no sense to ask whether the state rho hat B is entangled because system A is not subdivided. System B is also not subdivided. At least we are not subdividing it. So it only ever makes sense to ask whether a state is entangled or not if it's the state of a composite system that you subdivide it into subsystems. And system A and system B, we don't subdivide. Their only properties are, whether they have pure states or mixed states. But the big system, system AB, well, it can not only be pure or mixed, the big system can also be in an entangled state or not entangled state. And what we just saw is that if the big system here is in a pure state, and that pure state is unentangled, then our subsystems are also in pure states. Now, it turns out that you can also do this the other way around, namely that if the subsystem A is in a pure state, and you know that the big system is in a pure state, then the big system must also be in an unentangled state. Now, I give a proof of that in the lecture notes, but it would take us too long to actually go through that here. So let me summarize the key message here. Summary. Assume system AB is in a pure state omega. Then we have that if, and you know, i.e. rho hat AB equal to omega. Okay, then if rho hat A is pure, therefore the state rho hat AB, or because it's pure, I can just as well write it like this, omega is unentangled. And this also means that if rho hat A is mixed, then that's so if and only if the system, the big system, is in an entangled state. So let's keep that in mind. Mixedness of a subsystem is equivalent to entanglement in the supersystem, in the big system. Assuming that, I mean, we are always assuming for this lecture that the big system is in a pure state. Then we can unequivocally say that if a subsystem is in a mixed state, then the big system is in an entangled state, and vice versa. So what we see is that mixedness turns into entanglement, and entanglement turns into mixedness when we change the Heisenberg cut from a smaller system to a bigger system. This is perhaps surprising, because classically it's not like that at all. Remember what it means that a system is in a pure state. It means that we know everything that is knowable about the system. We know what state it is in, so we know everything that's knowable about the system. Imagine you know everything that's knowable about a house. Well, then you certainly also know everything that's knowable about its kitchen. And you know everything that's knowable about any one of the other rooms of the house. Right? If you know everything about the total, you should be also knowing everything about any subset of it. Not so quantum mechanically, because what we see here is that even if the big system is in a pure state, its subsystems can be mixed. They are mixed if and only if the big system is in an entangled state. But if the subsystem is in a mixed state, it means we don't quite know what state it is in. How come? How come that if we know everything about a house, there are still open questions about its kitchen? It seems to be weird. It's not so weird if you remember what entanglement means. Entanglement means that the state of the total system, I mean, the state of the total system is entangled if it is not just a tensor product of psi tensor phi, but a linear combination of such states. And that is non-local information. The information about entanglement is not contained in only one subsystem. Entanglement is a property that cannot be defined for subsystems, as we just pointed out. A subsystem itself doesn't have entanglement. It's the total system that has entanglement. And when you shrink your Heisenberg cut, then you lose that information. So in other words, there is non-local, non-trivial information about the state of the house, if we draw that analogy, which describes correlations between the kitchen and the dining room and other things. And if you consider only the kitchen and neglect those correlations, if you neglect these entanglement producing extra terms, then you don't know as much as would be knowable. And that's why the subsystem becomes mixed. It's a mixed state. Now it turns out that not only is it true that when you have a composite system that is in a pure state, which is entangled, then its subsystem, each of its two subsystems, is in a mixed state. No, there is also a dilation theorem. And that dilation theorem says it also works the other way around. If a subsystem is in a mixed state, or let's just say if any system is in a mixed state, then there always exists a practical, or at least hypothetical, Heisenberg cut such that the bigger system with this bigger Heisenberg cut is in a pure state. So what it says is, for every system A in a mixed state, rho hat A, there exists a system B and a, and this is important, and a pure state. A pure state rho hat AB of the total system such that rho hat A is indeed the trace of a subsystem B of rho hat AB. Just a sec, this is not trivial. You might think, sure, this is always true, right? This equation here is always true. Whenever you start with a system A and you add to it a system B, then the relationship between the density matrix of the subsystem A and the density matrix of the total system is always given by that equation. Nothing special about that. So what is the dilation theorem about? The dilation theorem says that the total state here is pure. That is super curious, because what it means is that when a system A is described as in a mixed state, so we have incomplete knowledge about it, then no matter what that system is, no matter how mixed its state is, there's always a Heisenberg cut that's larger, that contains our system plus extra stuff, such that that system with a bigger Heisenberg cut is in a pure state, which means that we should change to some extent what we think of what a mixed state is. When we first introduced mixed states, we did it naively, simply thinking, well, we often don't know what state the system is in. We can only assign probabilities to what state the system might be in. And then we describe these uncertainties, this lack of knowledge of what system the state might be in using a density matrix. And so we had a quantum and a classical source of uncertainty. Namely, there was the usual quantum uncertainty due to the uncertainty principle and quantum fluctuations and all that, but there was also uncertainty in predictions that came from us simply not knowing what state the system is in. Now we notice, because of the dilation theorem, that any such, in this sense, classical uncertainty, any classical ignorance, can in principle, at least mathematically, be ascribed to having made the Heisenberg cut too small. Let's say there is an experiment going on, and an experimenter is in the lab with the experiment, and the experimenter says, my system, I don't know what state it is in. I have to ascribe a mixed state to it. Mixed state. Well, what the dilation theorem says is you can enlarge the Heisenberg cut such that it encompasses the experiment and the experimenter and maybe parts of the lab and so on. But if you make it big enough, in principle, at least hypothetically, there's always a Heisenberg cut that includes the original experiment and then some hypothetical extra system, such that that bigger system in that bigger Heisenberg cut is in a pure state. Therefore, classical ignorance can always, at least mathematically, be described as arising from quantum ignorance. You just have to move the Heisenberg cut. Well, this is as far as we get today, and we will continue in this direction in the next lecture. See you then.